Alright, so we're going to pick up with our next section now and take a look at what happens once we've created pyruvate from glycolysis. And again, the assumption here is that we do have oxygen available, so we're going to move into aerobic cellular respiration, which is where the bulk of the ATP production is going to take place in this chapter. Alright, so the second big step that we're going to do is we're going to take the pyruvate created during glycolysis from the cytoplasm. We're going to transport it against the concentration gradient, and that by itself has some important implications for what it costs to do business with aerobic cellular respiration. We're going to move the pyruvate into the mitochondria, and we're going to oxidize it. Okay, so that's our next step. Glycolysis, at least, well, actually for all organisms, takes place in the cytoplasm, but for eukaryotic organisms, the next step, the Krebs cycle, takes place inside the mitochondria. And so to move pyruvate into the mitochondria, we are going to do some active transport. If we think back a few chapters and think about active transport, we know that it requires protein carriers, and we know that it requires energy. Right? So some of the energy that we're creating during cellular respiration is actually used to continue cellular respiration. It takes money to do. It takes money to make money, as the expression goes. So it takes energy to make energy in this case. We're going to use some ATP to make a bunch of ATP. To get the pyruvate into the mitochondria from the cytoplasm is going to cost some energy, but if we're willing to do that, we can then make far more energy than what we invest in the first place. All right, so we're going to have the next step. We're going to take pyruvate into the mitochondria. We're going to oxidize it, and that's going to give us, I know there's a series of products out of this which can be used in different ways inside the mitochondria, especially during electron transport chain and also during the Krebs cycle. So there's a multi-enzyme complex consisting of pyruvate dehydrogenase that catalyzes the reaction and allows this to continue. Right? So if we figure the products of this, what eventually is going to happen is that from the oxidation of pyruvate, we are going to get a single molecule of CO2, we are going to get one molecule of NADH, and we're going to get one molecule of what's called an acetyl group, which is a 2-carbon molecule joined to an enzyme called coenzyme A. And what this creates is an enzyme substrate complex called acetyl-CoA. So that's for each molecule of pyruvate, one CO2, one NADH, and one molecule of acetyl-CoA. That's after pyruvate's oxidized inside the mitochondria. All right, so if we go ahead and go back to our Word document for just a second that we started before in the first section, we're going to take now the next step of this process. We're going to say the oxidation of pyruvate, and we'll take a look at all the products involved, and that's going to be 2 molecules of CO2. It's going to give us 2 molecules of NADH, and those are going to go to the electron transport chain. And we're going to get 2 molecules of acetyl-CoA, and that then goes into the Krebs cycle. So I suppose what we could also do here is take a look at what happens to each of these products as the products are produced. So anytime we make ATP, it can be used by the cell. Anytime we make NADH, that's going to go to the electron transport chain, and when we make pyruvate, that's going to go to once they go into the mitochondria to be oxidized. Right? And so for the CO2 down here, anytime we're going to produce CO2, that is going to be removed from the cell or from the body, depending on what kind of organism we're looking at. So you're going to breathe it out effectively. NADH again goes to the ETC, and acetyl-CoA, as I said a second ago, is going to go on to the Krebs cycle, and that's going to take us to our next step, which will be the Krebs cycle, as we'll see here in just a second. We'll take a look at those products here momentarily. Okay, so again, inside the mitochondria, after we've oxidized the pyruvate, we're going to go to the next step, which is the Krebs cycle. We're going to take our 2-carbon acetyl groups, of which we made 2, and we're going to break those down to CO2 and several different electron carriers. Okay, so that is our next step. From those 2 acetyl-CoA molecules we made in the previous step, and remember, each acetyl-CoA molecule is 2 carbons. So for right here, we have a total of 4 carbons, and then, as we saw in our Word document a second ago, we already breathed out the other 2 carbons. Right? So we've accounted for all 6 carbons that came in initially with glucose. 2 of them have been breathed out as CO2. The other 4 are remaining as acetyl groups, but they're about to change their fate here in a second as well. So for our 2-carbon acetyl-CoA molecules, we are going to get our coenzyme A released. And so as we've seen before in previous chapters, enzymes, after they're used, get recycled, they get returned back to catalyze more reactions. So that enzyme goes back to being used again. We get 4 molecules of CO2, we get 2 molecules of ATP, we get 6 molecules of our electron carrier NADH, and we get 2 molecules of an electron carrier called FADH2, and that's the first time we've seen that one. So we'll go back to our Word document here in a second and take a look at what's going on with all these products. Okay, so let's go back here, and we're going to take a look at the Krebs cycle. So with the Krebs cycle, we get coenzyme A gets recycled and used again. We get 4 molecules of CO2, and those are going to be removed from the cell or from the body, again, depending on what kind of organism we're looking at. It's our subscript here as well. So our 2 molecules of CO2, we are going to get a grand total of 2 molecules of ATP, 2 ATPs, and those are used by the cell immediately. We're going to get 6 molecules of NADH, and those go to the ETC, and we get 2 molecules of FADH2, and those also go to the ETC. Right, so we're taking a look now at everything we've done so far and sort of keeping an ongoing total of everything that we've produced to this point. Now the other thing I wanted to do up here is I want to go back. We've already looked at the reduction of NAD+. I want to take a look at the reduction of a different molecule called FAD. And in a lot of ways it's very similar to what we saw before, a little bit of difference, but not really a whole lot. Okay, so we say FAD, and now we're going to add in kind of the same thing we saw before. So we're going to add in these things. Only now we're going to have 2 H pluses, 2 electrons, and the FAD, and that's going to give us a molecule of FADH2 as our reduced electron carrier. Okay, so again, the idea here is the same as we saw with NADH. The left to right arrow is going to be reduction. We're loading these electrons onto FAD. We are reducing it. So left to right is reduction. Right to left is going to be oxidation. So it's very similar in that regard to what we saw before. So a lot of chemistry in this chapter. We've got the overall equation itself. We've got the reduction of our 2 electron carriers. We have our 3 of 4 steps so far. We've got glycolysis. We've got the oxidation of pyruvate. And we have number 3, which is the Krebs cycle. That eventually then is going to lead us into step number 4, which is the electron transport chain and a related process called chemiosmosis, which we'll cover here momentarily. And so basically what step number 4 is going to do is to take all of our loaded up electron carriers and we're going to convert those to ATP. Okay, so that's going to be the next step. All right, so if we go ahead and take a look at what we've done so far, our grand totals to this point are this. We've created from glucose 6 molecules of CO2, and so what you'll notice, if you remember, is glucose is C6H12O6. We've gotten rid of all 6 carbons, so those have been accounted for. We've created only 4 molecules of ATP out of a theoretical total of 36. We've created 10 NADHs and 2 molecules of FADH2. Those molecules are then going to go to the electron transport chain where they're going to be oxidized, broken down, and used to make some ATP. So if we look at the overall grand total here, we've only released about 53 kilocalories per mole of energy coming into this so far. Right, so it's really not very much. A grand total of 686 kilocalories per mole. We've only released about 53 kilocalories. So most of the energy that started off in glucose of that 686 is still present in these 12 molecules of electron carriers here. The 53 is present in these 4 molecules of ATP, so a fairly small number so far. But once we get to the electron transport chain, that's going to serve as an energy converter. It's going to allow us to convert energy in the form of electrons in our electron carriers into energy in the form of ATP. And that's where the big payoff is going to be in terms of ATP, is during the electron transport chain. Right, so again, the Krebs cycle gives us 2 ATPs. We had 2 net ATPs also from glycolysis. We've only gotten 4 so far, but we need to get the other 30 in, and that's going to come from the reduced coenzymes, which are NADH and FADH2, during the electron transport chain. So these guys are all going to be oxidized, the electrons are moved, oxidized, and eventually energy is going to be released. All right, so before we move into the ETC, I want to make kind of a couple of analogies here as far as what these reduced coenzymes are like. And when I say, again, reduced coenzymes, that means NADH and FADH2. Right? They are very, very high energy molecules. They're good, they're great, they're very high quality energy, but our cells don't know how to use them directly. They have value, but our cells don't know how to utilize that value. It's kind of like if you went on vacation, came back, and you had a bunch of foreign currency in your pocket. It's worth money, but you can't spend it in the US. You don't want to throw it out because it's valuable, but on the other hand, you also can't spend it here. So if you were to go to Europe and come back with 100 euros in your pocket and need to go grocery shopping, so you go to Target or wherever to get your groceries, you walk in there and you go up to the cash register and you give them 100 euros, they're going to look at you like you're crazy. It's valuable currency, only that particular outlet doesn't take that currency. So what do you have to do? You have to go to a bank and you have to convert your euros back into US dollars. This is the exact same idea as what's happening inside of a cell. The reduced coenzymes, NADH and FADH2, are valuable, they're high energy, but our cells don't know how to utilize them for most activities. So we have to find a currency converter. Right? We have to find something which is able to convert the reduced coenzymes energy into ATP energy, which our cells do know how to use. The electron transport chain is kind of like the bank in that it's a currency converter. It allows us to convert energy in the form of NADH and FADH2 into ATP, which, like I said a second ago, our cells can actually use. So that takes us to step number 4. Right? We've got our electron transport chain, we've got our chemiosmosis, we've got our loaded up coenzymes, our reduced coenzymes. Now we're going to make use of them. And this is all taking place inside the mitochondrial membrane. All right, so the electron transport chain is kind of like a series of electron acceptors. Right? These electron acceptors pass electrons on one to the next, to the next, to the next, until eventually those electrons reach oxygen, which is the final electron acceptor. Okay, so the electrons coming off of NADH and FADH2. If we go back to our little Word document for a second here, we've got our loaded up electron carriers, NADH and FADH2. These two are the reduced forms. If we oxidize those, we get electrons back in both cases. And that's what we're trying to do here. We're trying to get our electrons back. And in the process, when we get our electrons back, we're also trying to get their energy back. Right? So that's our next step, is to get the energy back out of the electrons that we can actually use to manufacture some ATP. So a quick question. Where did the energy come from that's in those electrons? Well, think about where glucose came from. Glucose came from photosynthesis, which requires sunlight to produce. Remember, all the way back at the beginning of this chapter, I said that glucose is kind of like a battery for storing up sunlight. Now we're going to get the energy back out again. Photosynthesis charges the battery. Cellular respiration draws energy from the battery to make ATP. Okay, so our high energy reduced coenzymes are going to be given up. H pluses are also going to be given up. Hydrogen ions are going to be given up as well. And in the process, that's going to allow us to make some ATP. So basically what we're going to do is we're going to take all of these molecules over here and these the NADH and the FADH2, we're going to go back, we're going to get our NAD plus back, our H pluses back, our electrons back. Here we're going to get FAD, 2 H pluses, and 2 electrons back as well. So that's what we're doing during the electron transport chain, is reversing or oxidizing the molecules that we saw back in those different equations. All right, so what this is doing is taking electrons, which are high energy, and allowing them, for all intents and purposes, to go down an energy hill, to go from high energy to low energy. And as we know, since we can't destroy energy, the energy is converted to some other form, which is useful in this case to make ATP. Right? But we haven't seen yet where the energy goes or what it's used to do. Right? The energy in the electrons is actually used to do active transport of H pluses. Remember, active transport requires energy. The electrons contain energy. So as they give up their energy, that energy is used to move H pluses against their concentration gradient in a process, the beginning of a process called chemiosmosis. Right? So another thing to think about here is all the different kinds of things that cellular respiration does for the cell. Number one, obviously, it makes ATP. But that by itself really isn't the be-all and end-all of what cellular respiration is and what it does. Really what cellular respiration does is it helps us eventually get rid of these H pluses, because otherwise the inside of the mitochondria would begin to acidify. That would become very harmful to the enzymes in the mitochondria. That could be very problematic. So one of the other things that cellular respiration does is help our cells get rid of H pluses, actually in the form of water, as we'll see here a little bit later on. The other thing that this does is it helps us recycle our oxidized coenzymes back to the earlier stages of glycolysis, oxidation to pyruvate, and the Krebs cycle. Because to keep especially glycolysis going, you have to have a steady supply of NAD pluses. The electron transport chain gives us a steady supply of NAD pluses. So what we're actually going to do here is again, we've got our little notes page here. We're going to go back, and I want to make a note that says this, like, what does aerobic, if I could spell, cellular respiration accomplish? Well, there's 3 things, right? Number one, really the one we've talked about so far, is it creates a steady supply of ATP, which our cells then use to do all kinds of things, whether it's movement, whether it's division, whether it's production of proteins or fats, or really just about anything. Our cells use ATP for just about everything they do. The second thing that it does is it helps our cells dispose of H pluses. And those H pluses, again, if they build up too much, that effectively, really, by definition, is acidifying the inside of the mitochondria, which can be very problematic for the cell itself. And the third thing that it does is it recycles NAD plus back to especially glycolysis. That's especially important. But also the oxidation of pyruvate and the Krebs cycle. And to a lesser degree, I mean, it does that for FAD as well, but that's more important really only for the Krebs cycle. So that's really the crux of this chapter, is what this process does for our cells. And it's not just about making ATP. Glycolysis is really the most important one, so we're going to put a little star next to that one, because recycling NAD plus back to glycolysis is especially important in keeping glycolysis going. So the question about what cellular respiration does for us is actually answered 3 ways. It gives us energy, it helps us get rid of H pluses in the form of water, and helps us recycle NAD plus back into glycolysis especially. Right? So that's really a threefold answer as far as what this process does for us. Right, now, what the electron's energy is actually used to do, like I said a second ago, is to move H pluses against their concentration gradient. So what happens is that H pluses move from the matrix into the intramembrane space, and that's against a concentration gradient. It requires a protein. It is actually active transport. So that's where the energy gets spent that comes out of the electrons that were present in NADH and FADH2. So what we're doing here is we're setting up a concentration gradient of H pluses. The electrons come in the form of, say, NADH in this case. The electrons are given up. H pluses are given up as well, and NAD plus is released back into, say, glycolysis. And as this energy is given up, we're going to move H pluses from the matrix, which is the inner compartment of the mitochondria, out into the intramembrane space, which is the outer compartment of the mitochondria. And so every time these electrons get to a new acceptor, they give up a bit of energy, and that moves more H pluses from the matrix to the intramembrane space. And so what we're doing is we're creating a very, very steep concentration gradient of H pluses by continuously moving these things out into the intramembrane space. Eventually, these electrons come down here, they hook up with oxygen, they hook up with some H pluses from the matrix. That creates water. Right? So we know one of the products of cellular respiration is water. We had that back here in our little notes page. So if we go back up here, in the overall equation, we get CO2, and we get water out of aerobic cellular respiration. So that's where the water comes out, is the spent electrons, the H pluses, which are building up inside the mitochondria, and also the oxygen, which was present from our inhalation in the first place. That's the other part that makes up the water, right? So we're creating a very steep gradient of H pluses, and in the process, also creating a steady supply of water vapor. Right? And you know you get water vapor when you breathe out. If you hold up a piece of glass to your mouth, when you breathe out, you get condensation. So we know there's water vapor coming out there as well. Right? So we're doing active transport using a proton pump, moving H pluses from the matrix to the intramembrane space. And we're also creating water vapor by joining up electrons with H pluses and oxygen gas at the end of the ETC. All right, so we're going to actually stop here. This is a good place to cut off. This slide looks fairly ugly, so I'm going to pick up the next section with this slide and walk through it. It's really not as bad as what it looks the first time you see it, but it's a story. It's something you have to learn, like once upon a time there was blah, blah, blah. You learn it the same way. You start at the beginning, you walk through each of the steps, and eventually you get to the end of the story, which is right down here. This pink and purple blob represents an enzyme called ATP synthase here, which is actually used to make ATP. But before we get to this, we have to go through these other blue blobs first, and that's what we're going to pick up with our next section.